Shut up. This year would be my 25th high school reunion. I graduated high school 25 years ago in May.
Are you going?
Pardon?
Are you going to go?
No, I went to the 20th, but I haven't even heard word of a 25th. Either they don't want me there, or they're just not having one. But they had one. They have one at 20.
Was 25 depressing, or was the 20th one depressing?
No, it was fun. I
Yeah.
saw a lot of folks that I hadn't seen since that May at graduation. But you know, all the good ones you stay in touch with. So yeah, we're scattered to the four winds, but we still keep up with each other.
Well, Facebook, what's that?
Yeah, it does. It shortens the miles. Yeah, none of my best friends one best friend from high school, she still lives in Tuscaloosa. Everyone else is either in Florida, Georgia, Tennessee, or North Carolina.
Oh, I didn't go far then.
No, we're still in the South, so yeah, gotta make it home for Thanksgiving. Do you have any questions about this, or have you had a chance to start this yet? So if you've already done your retest, I guess that's the time to go ahead and crack into test form material. So a couple of you took yours today. Chauncey took his today too, so he'll probably start working on this soon.
Did a little bit of this weekend.
What was it with the vector fields and the gradient?
Oh, creating a vector field from a gradient?
Are they like perpendicular everywhere?
Yeah. What you do is you'll be given a function and you want to draw some of its level curves, or maybe the level curves will be graphed for you, and you say, you know, the gradient vector field will be perpendicular to the level curves, and longer where it's steeper, shorter where it's shallower steepness. So, but probably what I'm going to do for the vector field problem is say, here's a formula for a vector field. Which of these four represents its graph? A two-dimensional, not a three-dimensional. But what's a vector field again? You got time to learn that. You got time to get that down pat. Yeah. It's already 6:15. This is concerning. I guess a lot of folks are taking their test tonight.
Still studying.
It's kind of bad.
Yeah, it was bad.
I'm going to shut the door in the interest of keeping the funk at bay. Because this stings out there. What that is. So, if you're going to post this, Danielle, I appreciate it. This will be your rough outline. Rough in so much that I just hand wrote this about 20 minutes ago. Just going over I just rostered out the topics in black, and then sort of guesstimated, you know, what number of problems I could put. You know, one triple integral involving XYZ coordinates where you'll be given maybe the graph of a 3D surface and the equations that represent the parts of the surface, and do your Z limits, and then project it down and do your X and Y limits. And then one of each for a cylindrical and a spherical triple integral. Maybe one converting from rectangular into cylindrical or spherical, or maybe another where you're also given a graph and you want to set up the spherical limits or the cylindrical limits. But there's problems like this in that supplemental homework. Vector fields, given the equation for a vector field in 2 dimensions, choose which of the ones would match with its graph. Maybe graphing a few random vectors in the field to see which one has vectors that would align with that particular one. Line integrals, we started last week. Probably 2 problems, one involving a ds type, another involving a dx dy type, where you're given a parametric curve. Here's the line integral. And in both cases, they evaluate in terms of t. You'll always turn it into a t interval. And you'll be given a parametric equation. You know, the t limits for the parametric curve will become your limits on the integral. And then one problem involving the fundamental theorem of calculus, or fundamental theorem of line integrals. And that inherently ties in with conservative vector fields. You know, a conservative vector field, remember what that's all about?
Conservative. Yes.
What makes a vector field qualify as being conservative?
It's
it's right there. If the vector field was created by doing something to a scalar function.
Unitizing?
parameterizing.
Taking its gradient. A conservative vector field is the gradient of some little f of x and y. And so we talked about you doing the potential function for the vector field, the anti-gradient is what I roughly called it, given the layman's name. And so one problem involving that, and that'll probably, those are almost always F dot dr line integrals, so that's how F dot dr could show up on your test 4. One Green's theorem problem. Green's theorem is where you're evaluating a line integral over a closed loop. But what does Green's theorem turn the line integral into?
A 2D area.
A 2D area, a double integral over the inside area inside the loop curve.
So
Okay?
we can't always use it?
And you can use it, but you just need to remember Green's theorem's original form is intending counterclockwise orientation on your curve. If you happen to notice the orientation's clockwise, or if I'm generous enough to say, hey, by the way, notice the clockwise orientation here, you take the opposite of Green's theorem, it's double integral, okay?
It's just negative.
Pardon?
It's just negative.
Yeah, it's just the negative of your answer. If you do Green's theorem originally, but then you notice, oh wait, it's clockwise, just change the sign of your answer at the end.
Would you say conservative wasn't that?
A conservative vector field is a vector field that was created as a function's gradient. A conservative vector field has this property. There exists a function little f whose gradient is that vector field. Okay. So see, back in 2 tests ago, you were starting with little f and you created the gradient by doing the partial derivatives. Well, now you're starting with the vector field, and if it is conservative, then it's the gradient of some scalar function. You're kind of going backwards to find out what this little function is. What did the fundamental theorem tell you that you could do? Instead of doing the f dot dr integral the long way, where you had the parametric curve, replace the x's and y's with their t definitions, do that dot product with r prime, integrate with respect to t. Instead of doing that, if the vector field is conservative, you can find that little f function and do what with it?
Just plug in the values.
Plug in the values from your
2 points.
the 2 points that represent the beginning and end point of your path. So if in a conservative vector field, any path that connects point A to point B, whether it's a straight line or a semicircle or a sine wave or anything, would have the same line integral value when you do its f dot dr line integral. So the FTLI says you can find this little f function and do little f evaluated at your end point, plug in x, y there, minus little f evaluated at your begin point. And then what we're kicking into tonight, parametric surfaces and surface area are the 2 last official topics for test 4. What I'm going to do is the remaining topic that we had time for, surface interval flux. I'll go over that on Thursday night, but I will turn that into an optional bonus problem for test 4. So if you can't make it Thursday night, or if your brain is full after tonight, you don't have to worry about coming. So the official test 4 topic roster will end before we finish tonight. And you should anticipate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 problems on the test. Okay. Feel free to take a picture of this. It'll be posted online, but I just want to make sure everybody's got an idea of the format of the test. Jared?
I completely forgot when the retake test is going to cease being available.
Until Thursday.
Until Thursday?
But tomorrow's the last day they're open till 7:30, so you might want to jump at that.
When are they open on Thursday?
Thursday they close at 2. I think they open at 9 and they close at 2. And
That works for me. I've only got one class in the morning on Thursday, and it goes until like 10 something. So
Really throw me off my game, dude. I persevered.
do y'all have any other specific questions? Some of you have asked some questions about some of these things, but
I asked them so.
only a handful of you have asked like specific problems, like here's this triple integral I'm having trouble with. So try to get it all as polished and finished by Thursday, so we can do a pretty intense Q&A session before I do this flux stuff on Thursday night. Okay. And again, on test night, your test is a week from tonight. So those of you who are not attending class and not in the habit of attending class, test 4 will be. I'm speaking to the camera right now. Test 4 is going to be next Tuesday night. I'll be in here at 5 to go over any last minute questions you got. The test, we can start it at 6 or 6:15, just like class time, 2-hour time slot till 8:15 or however long you need to finish.
Is that Tuesday or Thursday?
Tuesday, no. My last final's on Wednesday. I want my grades turned in by Thursday, and then my summer will begin. Yes, sir.
You did, last class meeting, I believe you mentioned the possibility of the final being in the testing center. Is that still a possibility? Or
Can you do it by Wednesday? If you can do it by Wednesday,
I just
yes.
rather not have, I have my Chem 2 ACS final on Tuesday and other stuff, and I,
Yeah, so if anybody intends to take it in the testing center next week, let me know as soon as possible. I now know of 2 students who want to do it in the testing center. The last possible date I'm going to allow testing center testing is Wednesday of next week. Make it so. All right, make it fit. So tonight, we're starting into a topic that I never actually had in Calculus 3 when I was a student. I have learned this since being a Calculus 3 teacher. And it's dealing with how to parameterize a surface. The only parameterization you have done up to this point is parameterizing curves in space. Because essentially what you're doing is you're taking this, you're taking some t domain. T values here somewhere between 0 and 1. And then in 3 dimensions, if you let x, y, and z depend on this variable t like this, in this case, all the uses of t in these equations are linear, so this should give you a line segment that connects these 2 points. So you're essentially mapping, or in other words, you're sending values of t on this domain onto these 3-dimensional points on this line. So this particular t value that falls right here, see, this endpoint represents your t equals 0 stamp. This endpoint here represents your t equals 1 stamp for that line in space. So this point that looks like it's about 1/3 of the way from 0 to 1, maybe t equals 1/3, will probably fall right about here, 1/3 of the way from 0 to 1 on that line. And it looks like the orientation is in this direction, going from here to there. So you've dealt with parameterizing lines and curves in space. Whenever you parameterize some kind of curve in space like this, you only need 1 parameter. But because essentially the only real dimension here is its length. But if you want to parameterize a surface, something like down here, whenever you have a surface that you want to parameterize, you're technically starting in a 2-dimensional domain. And in most of my examples, I use the domain variables u and v. So like you may have some kind of rectangular patch in the UV plane that you can send out through these equations like this and maybe morph is a really weird word to use, or just map that 2-dimensional patch in the UV plane onto this part of the paraboloid. So in other words, through the use of these equations, you're transforming this patch into this surface out here in space, okay? And there's more than one way to parameterize a surface. I'm starting with a pretty straightforward example. One way to parameterize the paraboloid, there's the usual paraboloid equation you're accustomed to seeing, z equals x squared plus y squared, okay? I don't want to say it's the lamest parameterization. It is a parameterization, but I do think it's kind of lame. Because if you parameterize it in terms of u's and v's, if you let x be the variable u and let y be the variable v, since the equation of this paraboloid comes from z equals x squared plus y squared, you're defaulting z to having to become u squared plus v squared. And let me show you what this looks like on the computer when I graph it out. Because most software packages you find nowadays can actually do parametric graphing. If you recall, the way I had to do a parametric curve in space is I had to use a 3-component vector and then set it equal to, well, I don't know if I've actually done 3-component or curves in space with you guys. Like if I do this, 2 cosine t, 2 sine t, and then 0.25 t. Not a line, but anybody remember what that one might become? And again, I wasn't with you with this, so I'm not sure if you'll remember what this becomes in space when you actually graph it out.
Circle.
Okay, you got circle in the xy plane. X and y, depending on t, is 2 cosine and 2 sine will give you a circle of radius 2 in the xy plane. But then the z direction goes, so the xy motion is circular in the xy plane, but the z direction goes linearly, like this.
The corkscrew.
So it's going to give you well, it'll be actually a helix that's kind of on the outside of the cylinder of radius 2. So see, with only 1 parameter, that's going to give you a curve, like a line, or in this case, like a helix. Your t value goes from 0 to 1. So if t represents revolutions of a screw or a helix, somebody, well, no, I got a calculator here. I can do it my own self. 0 to 2 pi will give you 1 twist of of a helix going up like this. So if I let t go to 6.28-ish, and then, let me move this thing down. Well, no, it defaulted back to 1. Sorry about that. There we go. And let me do one more thing. There's something else that kind of helps out when you're graphing curves in space. I'm going to graph the XY plane, just because putting a surface on here helps to kind of stabilize your image. So see, there's the helix that we just graphed there in gray. And so looking down on it, you see the radius of 2 on a circle. And if I overlap it with that blue color, let me give it a darker color so we can look down on it like this. So see, ooh, pretty close. Y'all see that pretty well? Here's positive x. Sorry about the skewed view, but here's positive x, here's positive y. So looking down at the projection of this curve on the xy plane, you see a circle of radius 2. And see, the window variables over here tell you that x and y range from -2 to 2 in their direction. So that circle fits flush in this little patch of blue I have on the xy plane. But then, since t is growing linearly, or z is growing linearly, then you have this motion of circle in the xy plane, and it sort of grows up like this as t increases. So if I went from 0 to, let's see, what would 8 pi be? That's about 25.13. So I wanted to have a few more revolutions of my corkscrew. You can just increase your t value like that, and it just gives you more extra revolutions. So you see more of a spring effect with the helix going up, starting here on the positive x-axis and then spiraling upward like that.
So if it was a lot less than 1, then it'd be closer together?
Yeah, if I did 0.025 t, that would just tighten the coil. See, I got the 0.25 on there for z, so if you're right, if you sort of shrink that, make it 1/100, and that gives you a really tight coil. See, but it's still a helix. It's still growing. It's just, you're just shrinking it out. And then if you let it just be t, just sort of stretch it, or 2t or 3t. So any kind of curve you parameterize in space, this is essentially, even though this is in 3D, you're taking a one-dimensional domain from t equals 0 to 2 pi or 8 pi, and you're gradually plugging in t values one at a time to generate x, y, z coordinates in 3 dimensions. So the beginning value of t in the domain starts at the bottom of the corkscrew, and then the end value stops at the end of wherever your domain is restricted to. Now, parametric surfaces. The only one I've introduced you to so far is the paraboloid. So let me show you the way that's going to look. Okay, still need a 3 vector. And notice over here on these parameters, you've actually got the variables u and v used right here. Okay, so if I pair this up correctly, if I let x equal u and let y equal the variable v, and then if we want to parameterize the paraboloid, you let z equal x squared plus y squared, you just default to replacing x with u and y with v. So the z part of the parametric surface would be u squared plus v squared. Now, I want to change this over here. I don't want u and v to go from 0 to 1. I want it to at least kind of match the domain of my box here. This is the domain of xy space, the -2 to 2, this invisible box that we can see the surface in. So since u represents x and v represents y, I'm going to allow them to go from -2 to 2 also. Okay? So before I hit graph, -2 to 2, -2 to 2. Yeah, there we go. And so the reason I call this kind of a lame version of this parametric surface is because look at the Batman cape effect you get with the top end of this. Wherever the domain is cut by a rectangle in the xy plane, it sort of gives you that kind of, well, that's the only thing I can think of is I think of Batman's cape that has those little, sharp pointy things on it, all right? But if we skew our view to where we're looking down from the top, oh, so close. Close. I'll get it eventually. Problem thing is, this doesn't have a grab tool. Oh, close enough, I'm happy. This is the reason I consider this to be a pretty lame parameterization, because you're just pairing x with u and y with v. You're really just using the rectangular coordinate system, just replacing them with variables of u and v. So since x goes, in this window, x goes from -4 to 4. You know, that's what we see here. U goes from -2 to 2. There's that cut in the x direction, and then here's the -2 to 2 cut in the y direction. So you're really taking this paraboloid in space, but you're cutting it with a square domain when you parameterize it this way. I want to show you an alternative that uses a different coordinate system. Okay, so let me delete this, make a 3 vector. Let's do this pairing. Okay, and at first I'm just going to let z equal 0. U cosine v, U sine v. I want you to think r cosine theta, r sine theta. Okay, I'm just using the variables u and v in lieu, in place of r polar and theta polar. So if I'm wanting to generate something of a surface here, I'm going to let u, if it's playing the role of polar r, u is going to represent every radius I need, maybe from, well, in this case, it would represent a radius from -2 to 2. And even though that does make sense, I'm used to letting r start at 0. So let's let r start at 0, or let u start at 0. Excuse me. And then v is playing the role of polar theta. So since v is kind of like your polar theta variable, let it range from 0 to 2 pi. 6.28-ish. Well, up there above, there's a better approximation. Oh, sugar. 6.2831. Yeah, that's good enough. Okay, and whoa, what happened here? 0 to 2, 0 to 2 pi. That's not the image I'm wanting.
X goes from 1 to...
Oh crap, that changed too. Okay, thank you for noticing that. Let's go. Okay, there we go. That's what I want. All right. So this only becomes. This is essentially just a disk. If you look down on it, we're looking down. There's the z-axis trying to come toward us, so that's coming out of the board. There's the positive x-axis, the positive y-axis. So you see, in using a polar definition for your u's and your v's, you get more of a circular domain cut as opposed to that square cut that gives you the Batman cape effect on your surface. Okay, and I'm more fond of using this when you're parameterizing a surface, just because it just makes it a little bit prettier. I don't know, maybe it's lame, but it seems more aesthetically pleasing to me. But notice the way this works when you're using u and v in this polar mindset. U represents the polar radius r. So since u ranges from 0 to 2, that's giving me a completely, bless you, it's giving me a filled-in disk starting at a radius of 0 at the origin all the way to a radius of 2. And the reason it's going all the way around like this is because v is playing the role of polar theta, and it's allowing us to go from 0 to 2 pi. So for instance, if I took these restrictions over here, and remember v is playing the role of theta, if I allow v to do this, stop at 3.14, what would that do to my disk? Cuts it in half. And remember, it's still oriented the same way it was in trigonometry. Positive x-axis is theta equals 0, theta equals pi over 2, about 1.57, theta equals pi, about 3.14, 3 pi over 2, and 2 pi. So if I let v, which is my theta-ish variable, that would cut this in half. But if I leave 0 to 2 for r, that's still going to give me a completely filled in top half of this circle, you see? So, yeah. So it's still and the reason this is flat down here in the xy plane is because the only thing we've done for z is we say that the z coordinates that pair with the surface are always going to be z equals 0. So this surface has no chance to be anywhere but in the xy plane, you see? Okay. What if I wanted a strip that represents a radius of 1 and a radius of 2, like a half annulus going around here? What if, in other words, instead of giving me a full half circle from 0 to pi, what if I wanted a strip that represents a radius of 1 to a radius of 2 going all the way around?
U 1 to 2.
Let u, which is my polar r, let it go from 1 to 2, and that'll guarantee you're only going to see that part of the surface, you see? So knowing how to parameterize a surface I don't know how many of you have like computer modeling in your future, but the reason this probably got integrated into the Calc3 curriculum was probably because of computer, modeling, or even stuff like, this is probably the rudiments of Pixar animation. I have no idea. I have no idea, but you can animate things like this, like, there's a little animation parameter down here at the bottom of the screen. I think you can barely see it. It's this letter N. So if you tie that letter N into part of your surface, and according to this, you can hit this play button and allow N to slide through whatever values you've designated for it. So if I click on this N button, and I let the N minimum value, N's lowest value be 0, and N's top value be, say, 2, and let it go in 10 steps. So it'll go from 0 to 0.2 to 0.4 to up to, all the way up to 2. And then click OK. Since my Z depends on N, when I hit play, it'll give me that same disk and just sort of, slide it up and down like that. Not sure why I'm showing you this. I just, I mentioned Pixar animation, so I was like, let's show them something actually animated. So, but it's changing the Z values based on what your N slider value is going to, from 0 to 2 in those 0.2 increments like that. So anyway, I guess I'm being silly now. But yeah, that's the essence of parametric surfaces, is allowing you to use certain parts of your domain to give you that particular part of the graph. Now, if I want to graph a paraboloid is still generated from that same equation, z equals x squared plus y squared. So let me turn this light back for a second. Okay, but I'm not using rectangular coordinates anymore. I'm using polar coordinates. And I've already made a designation for what x and y stand for. So if you substitute the u cosine b for x and the u sine b for y, this will guarantee to give you a paraboloid, or at least some part of the paraboloid based on what you're using for u and b. You plug in u cosine b for x and the u sine b for y. They're squared. So what kicks in here? What does this eventually simplify to if you simplify it correctly?
R squared.
Well, you're thinking in polar, which is fine, because we've likened u here to polar r.
Your u, and then
Yeah, since that becomes u squared cosine squared plus u squared sine squared, and they're both the same arguments, cosine squared plus sine squared are both of v. If you factor the u squared out, the cosine squared plus sine squared combo goes to 1. So if you designate z here to just equal u squared, okay? Now, and let me go back to my original u's and v's. Let's let u go from 0 to 2, and v go from 0 to 2 pi-ish. So then looking down on this, notice there's a little slit in our graph. You see that? Oh, perfect alignment. I like that green x-axis perfectly. There's a hole right there, if you saw it. What do you think is causing that hole to be on that part of the graph? You see that little tiny little hairline discontinuity? Yeah, I mean, it's not a
for v is 6.28. So
because I've used a pretty raw value of v. Yeah, I've used 6.28 versus the preset value that the software has goes to at least 7 digits after the decimal. So if I use its approximation of 2 pi versus the 6.28, that will seal that up. Okay, but if you're looking down on the xy plane, I mean, this is still oh sweet good. This is still that disk that allows the radius u to go from 0 to 2. Okay, there's that circle of 0 to 2 radius. And v goes from 0 all the way around to 2 pi. Well, 2 pi-ish. We got a little discontinuity gap in the graph there, but it's pretty close to being sealed. But then the z coordinate, or the z component now, is not just 0. So it's not just a flat disk in the xy plane. The z component is based on z equals u squared, which came directly from the equation for this paraboloid. Okay? So, let me switch back to my document camera. Just to go back over the notes again. The first parameterization that we used for the paraboloid was, again, I'll go ahead and actually write the word lame here because it really is just kind of lame. Just because I don't like these Batman wing effects, these bat cape effects on the side of the graph. I'd much rather see a paraboloid that has a circular cross section because its horizontal cross section should be circles or at least ellipses. But if this surface is generated by that parameterization, x equals u, y equals v, and z equals u squared plus v squared, just doing the straightforward, taking the equation of the paraboloid and plugging in x equals u and y equals v, then what values of u and v would produce this image right here? Okay, this one is produced, this inequality looks a little loopy, but it tells you the image you see here is based on u and v going from -1 to 1. So since u is playing the role of the x variable, this end right here represents, u equals, or x equals 1, and this end over here comes down to y equals 1. This end back here projects down to -1 on the y-axis, and the one we can't see behind it there would project down to -1 on the x-axis. So that -1 to 1 cut in the y direction and in the x direction gives you that effect. And it's still the values of u and v, because u and v are the same as x and y. So what restrictions on u and v would give me this particular part of the paraboloid? Same orientation. This is still the positive x-axis. This is the positive y-axis.
So you would go from 0 to, if it's -1 is behind, so it would go from 0, or from -1 to 0.
Okay, so
U.
So u, yes, u is paired with x. Since u is paired with x, then the x values here are cut from -1 to 0. So
And then -1 to 1.
0, 0. So you can either give me an inequality -1 to u to 0 like this, or you could list it in interval notation. The interval -1 to 0 is what's giving me that portion that starts here and goes back to there, where u equals -1, because u equals x. And then what y values are used to produce this part of the image?
-1.
They didn't change. They're still -1 to 1 from that cut. So, because this is still going from -1 on y to +1 on y, y's values didn't change, so therefore v's values are still going to be -1 to 1. But the only thing that was cut was the positive x-axis half is gone. You only have the negative x-axis half. So since u equals x, you would want to restrict u to go from -1 to 0 to isolate just those negative x values on the graph of the paraboloid. Okay. Let me see if you can do this one. I switched from using the rectangular parameterization, where the rectangular parameterization is always just the lame one. Let x equal u and y equal v. And then if your equation is z equals x squared plus y to the 4th, then the parameterization will be z equals u squared plus v to the 4th. That's it. So I prefer using a circular domain that comes from kind of mimicking polar coordinates. And I've actually gone so far as to actually use r and theta here as opposed to u and v. So
Pi to 2 pi and 1 to 2.
yeah, for this one, oh, you already, I don't know. Let me check. I don't think it's actually going to be 1 to 2. You got to be careful. But you do have the pi to 2 pi part, right? Because positive x-axis is here. So apparently there's nothing in this paraboloid from the 0 to pi part of theta. But you start back here on the negative y-axis and it wraps around this way, so you wouldn't want to allow theta to go from pi to 2 pi. Does everybody see how that's true? Okay? Just because of the amount of rotation you got right there. Here to here, that's your theta, going from pi to 2 pi. Oops. But then double check your r values. It's really tempting to say r goes from 1 to 2, but anybody speculate something else for r?
Square root of 2?
R squared spans from 1 to 2, because these are actual z values. You're cutting the bottom at z equals 1, the top at z equals 2. Z does not equal r, z equals r squared. So when the bottom value is z equals 1, that would correspond to r squared equaling 1. So your first r value that produces that bottom part would be r equals 1. So that's right. But what's the top part that's going to give you a z value of 2? Square root of 2. Yeah. Because right here, z equals 1 means r squared equals 1. So r equals 1 if you just take the square root of that equation. But then the top part is where z equals 2. So take your parameterization. Z equals r squared. Set it equal to the 2 also. So that'll give you, just assume the positive root 2 without the plus or the minus. So r actually has to span from 1 to root 2 to give you that piece of the paraboloid. Okay. So this is kind of an abstract topic, but one favor I will afford you is